Okay, I'd like to see if I can clarify a few things and prepare us for Chapter 19, particularly in terms of some concepts and some notation. So Chapter 18 was about sampling distribution models. We're looking at how samples vary. And we did that activity in class where we looked at how far back the times of the women were in the NORAMs. And each of us took random samples of the 48 who finished, I think it was, and we would take a mean of that. And when we plotted all of our means, and then on Fathom we did it at least 100 samples, we recognized that we get a normal model. Now, just to back up, a lot of the questions say, well, what are the assumptions and conditions? In other words, how do we know we can use a normal model? And there's two things we're interested in. We want to make sure that each sample is independent of the next. We're looking for independence, and we want to make sure that the sample size is large enough. Now, how can we check independence? Well, if it's a random sample and we're sampling less than 10%, then we can assume that each measure in the sample is independent of the next. How do we know if our sample size is large enough? Well, for proportions, we can actually check that. If we take our sample size and measure by the proportion of successes, if we can get at least 10 successes and at least 10 failures, we say our sample size is large enough. For means, we really just have to make an educated guess. Do we think that our sample size is large enough to be represented and produce a normal model? The more skewed the original population, the larger you probably would want your sample size. So that's all about the assumptions. We make these assumptions, and then we can actually check conditions to rationalize our assumptions. Okay, so what's going on here? A sampling distribution of proportions looks like this. The sample proportions will stack up around the true proportion P, and the standard deviation of this model is equal to the square root of your true proportion times proportion of successes times proportion of failures divided by your sample size. So suppose the CDC reports that 22% of 18-year-old American women have a BMI that suggests they will have health risks. But then I go out and ask students to 18-year-old people to self-report. I ask 200 of them, and it turns out that only 16% of them have a BMI that would indicate health risks. I'm going to know how likely is that to happen if this is the true proportion. So I first need to calculate. You might have had to calculate your actual proportion by saying this many out of 200, but anyway, you might have to actually calculate your sample proportion. So I need to know what my model looks like. So I already know my expected proportion is 22%. So I calculate the standard deviation. 22% times 78% divided by 200 square root works out to be 0.029. So I want to know how unusual this is. I calculate a z-score, my sample minus my expected divided by my standard deviation. It tells me that this is a little more than 2 standard deviations away from what I expected. Now, we already know that's fairly unusual. So we might say, well, either this was an unusual population of 18-year-old women, or maybe their self-reporting was not quite honest. Lots of other things, but that's how the proportion model works. I didn't calculate the likelihood of this happening. We already know this is not very likely. If we think about 2 standard deviations, we know this is 95% of the curve, so each end can only have 2.5%. So we know this is less than 2.5% likely to happen just due to natural variability. We're going to get more into that in a little while. What if we're talking about means? Well, again, here's a little more specific data. If we think the mean weight of 18-year-old women is 144, that's what we think it is, and we go out and take a sample of 200 and find that it's the mean of that sample is 140. Again, what's the likelihood? Is that can that be expected just due to natural variation? So my means model has my expected mean, and in this case, the standard deviation of a sampling model is going to be smaller than the standard deviation of the population. If you think about it, if you could collect the weights of every 18-year-old female in the country, there would be a lot of variability. If you go out and take samples and take the mean of those samples and then plot all those means, there's going to be less variation. So that's why I take the population standard deviation and divide by the square root of your sample size. So in this case, the expected mean was 144 pounds with a standard deviation of 51 pounds. So I need to calculate the standard deviation from my model, and I do that by my population standard deviation divided by the square root of my sample size, and I get the standard deviation of my sampling distribution is 3.6. And so again, here's my model. I have 144 pounds. My sample produced a mean of 140. How unusual is that? My sample minus my expected divided by my standard deviation. Turns out I'm only one standard deviation below what I expected. That's not very unusual. And to remind you how you would do that, you'd put that in your calculator, find a cumulative value of the normal model from negative 99 standard deviations, that's way down here, to negative 1.1 standard deviations, which is where this showed up with a mean of 0 and a standard deviation of 1. And I find out that that's about 13.3% likely to get a sample that produces a mean of 140 if the actual mean is 144. Does not seem very unusual. So that's the fundamental foundation for proportions and means and sampling distributions, how samples vary.